Next, we would like to study isomorphism between rings. But before that, we are going to define the notion called ideal. So here's the definition. Let R be a ring and I be an additive subgroup of R. Okay, remember, a ring can be regarded as a group when so ring has two operations that is addition and multiplication, and if we consider only the addition part, then the ring can be considered as a group, additive group. Therefore, we may be able to define an additive subgroup of R in this way. So let I be such a subgroup. And then, uh, if so, first, if for all elements in R and all elements A in I, if we have x times A also belongs to R, then we say R I is a left ideal of R. Okay, and 2, similarly, for all elements x in R and all elements A in I, if we have AX is an element of I, then we say I is a right ideal of R. And 3, for all elements in X and elements in I, if we have both AX is an element of I and XA is an element of I, then we say I is a two-sided ideal. Or simply just ideal, an ideal of R. So if we just say an ideal of R, that means two-sided ideal. Okay. And if we have a ring R, then the set consisting of only its zero element and R itself, these are ideals. These are trivial ideals. And non-trivial ideals, trivial ideals are subset of R that are proper subset of R, and that is also ideal. So these are called proper ideals, or proper left ideals, proper right ideals, proper two-sided ideals. So ideals are something that are similar to normal subgroups in the case of group theory, but ideals are for rings instead of groups. Let's see an example. Uh, so we have the set of integers. This is a ring. Okay, then nz, that is the set of multiples of n's. So that are nx, where uh, x is integer and n is a given integer. Okay, then this is an ideal. of Z. And this is two-sided ideal. And in general, for a commutative ring, and Z is a commutative ring. In the case of commutative rings, left or right ideals are also two-sided ideals. To see this is an ideal, it's very easy. So let's take any x from Z and any, let's say, a from nz. And of course, a is a multiple of n. So, for example, xa is a multiple of n. So, therefore, it's an element of nz. So, this is an ideal. And another example, and let's say m to q is a set of 2 by 2 matrices where all elements are rational numbers. And if we define L as the set of 2 by 2 matrices of this form, 0, P, 0, Q, and PQ are rational numbers, then we can see that this L is an additive subgroup of M2 of Q, because if we add two matrices of this form, it still has this form. So 1, 1, and 2 1 elements are both 0 if we add matrices of this type. And if we multiply any matrix, 2 by 2 matrix, with this type of matrix, then so A, B, so that's 0, A, P, B, Q, C, D, that's 0, and C, P, and D, Q. So this is an element of L. So we can see that this L is a ideal, a left ideal. Now let's see the following lemma. Okay, let R be a ring with the identity element 1, and let I be a non-zero left ideal. By the way, zero ideal means the ideal consisting of the zero element. So that means in this case, I is supposed to be a non-zero left ideal. So it contains something more than just zero element. Okay. Okay. Then if I contains a unit of R, then this ideal is left ideal is equal to the ring itself. Okay, so this is 1 and 2. A field is a ring, special type of ring. A field has no proper ideal, proper left or right ideals. Okay, by the way, again, this unit, what is a unit of a ring? It means an invertible element of the ring. So an element that has its multiplicative inverse. Okay. Okay, let's prove this. Oops. Okay, first let U be a unit of R. Then there exists some element, let's say V, in R such that UV is equal to the identity element. Okay, so for any element in R, we have x is equal to x times 1, which is equal to x times uv. Okay, so this means by associativity we have xu of v, and this is an element of the ideal, because that's the definition of ideal. Okay, so that means any element is an element of the ideal. Any element of the ring is an element of ideal. Therefore, uh, therefore this ideal is equal to the ring itself. And the second part follows very easily from the first part because every non-zero element of a field is a unit. Of a field is a unit. So that means every non-zero element of a field is invertible. So from part 1, there cannot be any proper right or left ideals. And we are done. Let's see an example. Before we consider this set of 2 by 2 matrices over rational numbers, and we have seen there exists at least one left proper ideal that was of this form, right? So this was a left ideal. But now we show that there are no proper two-sided ideals of this ring. Okay, suppose I is a non-zero two-sided ideal of M2 of Q, and suppose A, B, C, D is a non-zero element of I, and A, B, C, D is non-zero. Okay, so at least one of A, B, C, D is not zero. So for the sake of argument, suppose A is not equal to zero. Then we have A over B, B over A. Since A is assumed to be non-zero, we can do this. B over A is fine. And 0, 0. This is expressed as a product of these two matrices. 1 over A, 0, 0, 0 times A, B, C, D. And this A, B, C, D, this matrix is an element of ideal. So since we are assuming that this I is a two-sided ideal, then this should be an element of I. So therefore this matrix is an element of this ideal. Okay, but now using this matrix we can express 1, 0, 0, 1, 1, 0, 0, 0 as a product of these two matrices. Okay, so now we're assuming I is a two-sided ideal. So if we multiply any element of any two by two matrix with an element of I, then it should belong to I, the ideal. So therefore, this matrix 1, 0, 0, 0 is an element of I. So similarly, we can show that 0, 1, 0, 0 and 0, 0, 1, 0 and 0, 0, 0, 1 are elements of I. Right? So just like this, assume B is non-zero, then we can show this is an element of I. Assuming C is not zero, then this is an element of I, and so on. So since all of these four matrices are elements of I, we can express any matrix X, Y, Z, W as follows. So X. So basically, let's see. So X 0, 0, 0 plus 0, Y 0, 0 plus 0, 0, Z 0 plus 0, 0, 0, W, and that is, so this one is X 0, 0, X 1, 0, 0, 0 and Y 0, 1, 0, 0 and Z 0, Z 0, 0, 1, 0 W 0, 0, W 0, 0, 0, 1. So that means, so we have seen this, this and this and this, and these are all elements of ideal I, the ideal I, and ideal is by definition an additive subgroup. So therefore, this belongs to the ideal I. So in other words, any matrix, any 2 by 2 matrix is an element of I. So therefore, this ideal is actually the same as the set of 2 by 2 matrices of a Q. Therefore, this ideal is not a proper ideal. Now, let's see the following theorem. Let R be a ring. And first, let A be an element of R. Then if we define a set Ra by x times A, where x is an element of R, then this is a left ideal. Of R. And second, if let n1, l2, and so on, and ln be left ideals of R, then if we define the following set, n1 plus l2 plus and so on plus ln as a1, a2, so any element of R that can be expressed as a sum of elements of these ideals. Is again a left ideal. And by combining the part 1 and part 2, we have the following. Let A1, A2, AN be elements of the ring. Then RA1, RA2, and RAN defined as x1, a1, x2, a2, xn times an, where xi is any element of R and ai is an element of not I is from 1 to n, is a left ideal. So let's prove this. In part 1, first of all, 0 is equal to 0 times a, which is an element of Ra. And for any x1, x2, and y that are elements of R, we have x1 times a and x2 times a. So since we are considering a ring, we can use distributive law, and that is x1 plus x2 times a, which is an element of Ra. So some element of R times a. So it's an element of Ra. And also negative x1 a. Okay, we don't need, so negative ya is equal to negative y times a, which is clearly an element of Ra. So therefore Ra is a left ideal. Well, maybe there is a jump in logic here, but so these two proves that Ra is an additive subgroup of R. But if we pick any elements x from the ring and multiply, let's say, and any elements in Ra can be expressed as ya. So x times ya is xya, which is an element of Ra. So this really proves that Ra is a left ideal. Okay. For part 2, instead of dealing with n ideals, we just prove for 2 ideals. And for general number of ideals, we can just use simple induction, mathematical induction. So let's say, suppose A, B are left ideals of R. Then A plus B is defined as elements, set of elements that can be expressed as A plus B, where A is an element of A and B is an element of B. And this, it's easy to show that this is an additive subgroup. So you should apply the subgroup criterion for this. So existence of 0, closed under addition, and the existence of the additive inverse, these can be all satisfied. So anyway, let X be any element of the ring, and A an element of A and B an element of B. Then X times A plus B is XA plus XB. But since this A and B, this B, are left ideals, so this belongs to A and XB belongs to B. Therefore, this belongs to A plus B. Therefore, A plus B is a left ideal of R. And we skip the proof of 3. I will just say obvious from part 1 and part 2. 1 and 2. And we are done.